including quantum ones, and carried out at the Institute for Metal Physics and in Academic University, Kyiv Academic University, with collaboration with other institutions of Ukraine and other countries. I hope that my English will not be a problem to communicate. And so I started. Our department was created in 1957. It relatively young department in our institute. From our creation, our investigation were concerned with the problem of the formation of the atomic and electrical structure of metal and alloys, the influence of interfaces and defects on the mechanical, thermal, optical, magnetic, and electrical properties of material, particularly for energy application. Over time, the subject has been extended to the nanomaterials and quantum materials. Today, the main direction of the department's work are the following. All of these areas need to know and engineering of materials work function value, including their lowering. The first, what I need to say about our investigation of quantum materials is the next. We developed the method for the generalization, cluster, and expansion of green function, which make it possible to study the future of electron spectra in direct and reciprocal spaces associated with the manifesting properties of strongly correlated alloys for different components, parameters, and various types and degrees of atomic and magnetic ordering. The arbitrary degree of ordering is inaccessible for the first principle methods like DFT. And we can do it. We also investigate materials for high and low temperature thermionic converters. For the last, the operating temperature are 170, 350 degree of Celsius. That are 3-5 times lower than ones of traditional refractory metals. To reduce work function and corresponding operating temperatures in such systems, cesium atoms are used. They fill a vacuum gap between electrodes and absorbed on their surfaces. However, due to the high chemical activity of cesium, it is very difficult to retain it on the surface of the electrodes. Therefore, we search the system that would allow binding cesium on the surface, in particular, system based on multi-layered graphene. Today I will present the results of theoretical studies that have been carried out in close collaboration between the Department of Electronic Structure and Electronic Properties of Institute for Metal Physics and Department of Applied Physics and Nanomaterials of Kyiv Academic University and the Group of Condensed Matter Theory of the University of Zurich. We investigate the work function of materials. I mean the energy that needs to be provided to electrons in the system to move them away from the surface over a sufficiently large distance. In metals at 0 Kelvin, this will be the difference between the Fermi level and the vacuum level. The efficiency of catalysis process, vacuum electronics, energy harvesting, and solid-state electronics directly depends on the value of work function. Work function play the sufficiently role in emission properties of materials. It stay in exponent and determine the possibility of electron exit from material. We must to control the work function of various materials. So what are the way to implement such control? The first is associated with change in the position of the Fermi level in the system due to doping or by changing the electronic structure itself. For example, through chemical composition and deformation, including from defects. If a perpendicular electric field is applied to surface, the Schottky effect reduces the highest and width of the potential barrier and correspondingly reduce the effective work function by value delta F. It also increases a contribution to temperature independent field emission due to the tunneling of electrons through the potential barrier. Second, a similar results to the Schottky effect can be obtained due to creating a surface dipole moment, which generates its own electric field, which can increase or decrease the work function of the material. And multi-layer graphene allows to synchronous application of both mechanisms of the work function changing. Firstly, it can be intercalated with atoms, for example, alkali metals, which allows to mechanism associated with the Fermi level shift. Secondary, the idea of polar atomic such these complexes, for example, of alkali metal and oxygen atoms, which can be fixed between the layer of bilayer graphene and reduce the work function due to the surface dipoles formation. Such variant is known in literature, but our investigation have shown that it not realized. For our DFT calculation, we use the Quantum Espresso software package with the PBS exchange correlation functional, the dipole compensation, and the van der Waals correction. Relaxation was performed for all structure. In nature, there are two types of bilayer graphene, AB, like this, and AA, like this. They have relatively big work function. The graphs shows the difference between Fermi level and vacuum level for such system, and it is work function. In the case of AB graphene, we can intercalate it with alkali metals. In our case, it is cesium. The work function for maximal value of concentration of intercalant must be shifted very strongly, but we find that the changes are small because they are present deformation of the lattice structure of such graphene, but such structure are helps to AA graphene to be more stable than AB graphene. If we reduce the cesium concentration to 1 atom per 4 cells, it leads to a significant weakening of the lateral strain in the AA graphene and to a 0.36 electron volt decrease in the work function compared to the pure material. By creating near surface dipoles of different orientation, it is possible to both decrease and increase the value of work function. For example, the appearance of oxygen, it's red balls, atoms on the surface of graphene increase the value of work function. For example, the addition to oxygen, the cesium atoms, and formation of dipoles like this, we can decrease the work function to the value of 2.19 electron volts. The same effects is observed for AA graphene for both type of graphene. The work function is about 5 electron volts. When we add the vacancies in the concentration of 25%. The work function is closed for AA and AB graphene. In contrast to defect-free AB graphene, oxygen atoms decrease the work function because of partially filling the vacancy. By adding cesium atoms to the oxygen, the work function can be reduced to value 2.33 electron volts. The most interesting result was obtained for cesium intercalated defect-free AB graphene with an oxygen cesium atomic complex on the surface. In addition to the lowest value of the work function of 1.19 electron volts, we can see that the top cesium atoms is relatively close to the oxygen atom, and oxygen atom is close to the carbon one. That is in contrast to the previous cases when the oxygen cesium complexes form typically van der Waals bonds. In this case, a covalent bonds is possible. We also investigate the two-dimensional material contained graphene monolayer with atomic complex oxygen cesium. The fact that these materials is metallic and has an anomalous 1.2 electron volts work function suggest it could be a promising candidate for use as a tip in scanning tunneling microscope, field emission cathodes, and so on. One can also see the Fermi surface and which contains the some zones with nesting. Such geometry could lead to instabilities, potentially making the material instability to charge density waves or spin density waves. Therefore, these materials may serve as an exciting platform to study the interplay of different orders in two-dimensional systems. I present that my conclusion during the report, so I will skip them now. Thank you for your attention.
Thank you. If you have any questions, please. No questions. Okay. Good. Thank you. The next speaker, Ren. Yes. Okay.
Right.
Grain boundary modifications, yeah. Yes.
Maybe I can change it to. Okay, so good afternoon. Thank you so much for coming to my talk. And also thank you for the introduction. My name is Ran He. I'm currently working at IFW Dresden and as a group leader with Professor Cornelius Nilsch. So today, it's my great pleasure to have this opportunity to share this research topics we are recently have been paid a lot of attention to, which is concerning how we can modify the grain boundaries to change the transport properties and optimize the thermoelectric materials. So before I go to details, I want to make a brief introduction of these research activities we have. One group is led by Dr. Pérez, and he's also give a talk after me. He will also give introduction to this transport properties measurements using the PPMs system. Another group is led by Dr. Heiko Theis, and his group basically dealing with the research activities of using of micro devices. So regardless of for power generation or for cooling. So basically they are doing electrochemical deposition and following lithography pattern. And so then another group, not completely thermoelectric, but basically led by Dr. Amin Bahami. His group is dealing with surface modifications through for functionalized materials, such as not only for thermoelectrics, but also for some other technologies such as batteries. And next is one group led by Dr. Pinjun In. Basically, her group is dealing with all kinds of module activities. We fabricate the materials and we try to integrate these materials into the modules. So this complicated, somehow complicated interface designs and to fabricate the module. And we also do this, let's say, LD coating together with Dr. Amin Bahami to protect the modules, and we test in the cycling performance and to see how we can extend the lifetime of these devices. Another activity also is to using 3D printing, laser-based 3D printing to fabricate devices with advantage of you can arbitrarily change the leg geometry so that you can have this 1 degree of freedom to optimize the performance on module levels. Then finally come to introduction of my own group. I have my group is basically dealing with nanostructured bulk materials and using powder metallurgy basically preparations. We have activities dealing with how we can synthesize materials using basically non-equilibrium approaches. And for some material that is particularly of interest, we study the microstructure and we study the processing structure and property relations. And also we have this also involved in these module activities and together with Dr. In. And then one important topic of great interest for us is to modify the grain boundaries. And we recently started to put a lot of efforts into this and some preliminary results, which is also already very promising. And this is going to be the topic of my talk today. So a brief introduction of this background. So as you can see, if the carrier concentration dependent transport properties of the individual electroconductivity, the Seebeck coefficient, and thermal conductivity, we will see that they have all these kind of curves and they have a strong intercorrelation with each other. And it has been very challenging for the community in general to how to improve the performance, like the figure of merit ZT, to boost it. And if we look at deeper into these curves, and what we can see is that we can look at this Boltzmann formalism, and the conductivity is increasing with higher carrier concentration because we have a higher density of states. Meanwhile, for the Seebeck coefficient, there is a decisive term that is a factor that is the E minus EF. Basically, it means that when you change the energy of the carrier across the Fermi level, you're going to have a sign change of the Seebeck coefficient. So that means different charge carriers will counteract with each other. So you will not get a very high Seebeck coefficient. So that's why we need to have a band gap, because we can reduce, we can minimize the carriers from the one side of the Fermi level. so we can ensure that seebeck is high enough. So if we take a look at this multiplication of the energy density of states, electronic density of states, times the energy derivative of the Fermi distribution function, we can get something termed as the transport window. And so if you follow in the regular doping process, you're actually adding or removing electrons from the top of this window. And by doing that, you're going to follow these trends exactly. And you're going to have a limited value of ZT, and it's very difficult to further boost it. So in order to break this limit of and to get a higher performance of ZT, an alternative way is instead of play the charge carriers from the top of this window, we can try to figure out a way to play with the bottom of the window. And this way we could effectively increase the term E minus EF, and we can have a higher seebeck coefficient. And this could be realized in real materials, like because there's a lot of green boundaries, and these green boundaries could be serving as the scattering center to effectively scattering these lower energy charge carriers to enable these higher energies charge carriers could have a transport, meanwhile blocking these low energy charge carriers. And of course, this is a physics picture, a simple physics picture of the energy filter effect. People have been talking quite some time in the community. And if we want to get more detailed guidelines of how we can realize a performance gain, we have to play with the math. And there are several groups has already done this kind of work. And basically, the conclusion drawn from these works is that you need to several requirements, such as we need to have a high Fermi level, basically means heavy dope or even metallic materials. And the barrier height has to be even higher, but not too much, but slightly higher than this Fermi level. And also we need to have a wide barrier width to effectively reduce the tunneling effect. So this combines together, you could have the opportunity to enhance the thermoelectric performance. And indeed, there are some simulation work. This is based on N-type silicon. As you can see that we can indeed obtain a performance gain. This is term called power factor if you're not familiar with thermoelectrics. You can have a performance gain when the barrier is high enough, but only for the material that has a heavy doping. So that means these requirements could indeed have this opportunity to improve the performance. However, there is always however here. These three requirements are contradictory to each other. For example, when the material you have a high Fermi level, usually means this charge carrier interaction is strong, and this whatever boundary you have at the green boundary or whatever boundaries, they'll be effectively screened. So that means the charge carriers will not see these barriers when the number of them is too much. So that means you cannot effectively induce this effect. So is there any possibility that we can mitigate this contradiction? So we come up with the idea of that. We can still choose a material that has a high Fermi level. Which basically means heavy doping semiconductor or even the metallic material. And then we can extrinsically increase the barrier height by adding, for example, a resistive barrier, even like oxides. So with this idea, we come to use this technology called atomic layer deposition to coating the green boundaries. And so this is, if you are not familiar with this technology, the brief introduction it's a deposition technology by cycles. And you have two precursors, you purge and pump in one cycle, and then do the same process to a second precursor. And this way, you can effectively coating these layer materials, coating the layer one by two half layers. And this is a self-limiting effect, so you can ensure that the growth is uniform, and you can ensure that this is the thickness is uniform growth and controllable. So with these ideas, with this technology in hand, and we're starting from the metallic material. The most famous metallic thermoelectric material, of course, is copper nickel. And we take this material and we do coating using atomic layer deposition by either zinc oxides or aluminum oxide. And also we do multiple coatings, layered zinc oxide and aluminum oxide to tune the coating properties. And you can see that, we can see this is after the, we can see the coating of zinc oxide, but not aluminum oxide, because aluminum oxide is amorphous material. And we can see the coating through the mapping. You can see very, very uniform coating. And also even after centering, we can see the patterning of oxygen follows very nicely at the boundaries. So that means we could effectively coating the surfaces of these particles and to form some kind of scattering effect. And we look at the transport. I mean, here is an example of zinc oxide. And also, if we go, we can also look at aluminum oxide and also layered material, but that's too much information. This work has been published here, and if you're interested, of course, you can go read it. And for zinc oxide, what we can see is with coating, we decrease the conductivity, increase the resistivity, and also, of course, which is also accompanied by a very obvious enhancement of the Seebeck coefficient, and which combines together give us a performance gain in terms of power factor. And also thermal conductivity is decreased because of the enhanced electric resistivity. So the charge carriers is scattered more. So the heat is accompanying is also reduced. At the end of the day, we could see there is a performance gain in terms of ZT if we use this technology. Okay, so everything works fine for the metallic materials, but how about semiconductors? And particularly, we're interested in degenerate semiconductors, right? And this is a very recent work. We have been we just submitted, still in the process of review. Basically, it's dealing with rare earth carbonites, yttrium telluride. And this material has initially been predicted through a machine learning assisted calculation, then following much more detailed calculation for the band structures. And you could see that N-type material has a value degeneracy at the valence band, conduction band minimum. So that means it's predicted to be a very good N-type property. And what we did is that if we decrease the nominal amounts of tellurium, we could effectively enhance the electroconductivity. Meanwhile, it corresponds to a decrease of the Seebeck coefficient. At the end of the day, we could see that the material has a ZT around 0.5, 0.55 something, which is a decent material, but not very impressive. So then we can ask the question, what could grain boundary modification do to this property, to the properties of this material? And what we see is, what we did is that we can add in some bismuth to the nominal composition. And what we found is that when we add in this bismuth, we could see that bismuth does not really dissolve into the lattice. Instead, it forms these segregated particles. And simultaneously, there is also a formation of this some line structure, line profile. You can see there is also some contrast along these grain boundaries. And this is, of course, changes the microstructure fundamentally. And if you look at a mapping across the grain boundary, you could see that there is an enrichment of yttrium as well as enrichment of bismuth. So actually, the bismuth enables a grain boundary modification by reacting with some yttrium, and also corresponds to depletion of tellurium. And with this structure change, we could see something quite surprisingly, that there is an enhancement of the Seebeck coefficient by a factor of 4, which is really impressive when we initially see this result. But of course, it corresponds to a decrease of the conductivity, also by a factor of around 4. But since the Seebeck coefficient, we have a square here. And so at the end of the day, we still get a power factor improvement, also by a factor of 4 at around room temperature. Following the whole measurement, we can try to understand what is the mechanisms here. And basically what we can see is that after bismuth incorporation, the mobility has been greatly improved in comparison to the bismuth-free compounds. So at the end of the day, we can see the figure of merit ZT has a significant improvement from initially around 0.4 by a factor of 2, reaching like 1, even 1.2. I mean, still you can see this is increasing trend. So it means it could be higher at even higher temperatures. Yeah, that's for this part of work. Okay, and also somehow out of expectation, but not surprising, is that we check this material after this grain boundary modification, and we see that when we have this initially, when we don't have this coating, let's say just yttrium telluride, you see this material is reactive with water, and it is gradually like dissolve into water and with some bubble formation. I'm not so sure you can see it, but there is some bubbles formation here. But after we have been coated this material by bismuth, grain boundary by bismuth, the reaction rate has been significantly reduced. And after 10 minutes soaking in water with different concentration of bismuth, you can see that whenever we have some bismuth here, it's much more stable than the bismuth-free compounds. So this green boundary could also indeed effectively improve the material stability. Okay, Then that's part of the story, but there's another half of the story. So usually we would think that green boundaries is a charge carrier center. And the smaller green size, you will have a stronger scattering for charge carriers and the lower resistance, or the higher the resistance, sorry. But we also found that in some special materials, the trend is opposite. For example, this is a half-poisson material, titanium, cobalt, antimony. And we could replace, let's say, 30% iron at the cobalt site, and we can change the centering temperature in the centering process, and we can increase the temperature and increase the grain size. But what's surprisingly, what people has been found is that when you have a largest grain size, the conductivity turns out to be the smallest, which is quite counterintuitive. Similarly, people has also been trying to play with another material and also half-poisson is niobium cobalt tin. People do platinum doping at the cobalt site, 5%. And it found that with this doping process, platinum does not really enter the lattice, but instead it segregates at the grain boundaries. And you can see from the mapping, this platinum follows these grain boundaries. And then these people have this technology to do this local probing of the conductance. So what was found is that if you measure the local resistance across a grain boundary, the conductivity is actually higher than you do the similar measurements in the grain interior. So that means the grain boundary itself is not only a source for charge carrier scattering, but could also be a transport path that can promote overall conductance of this material. So with this knowledge, we take my own materials, which I have developed like back in 8 years ago, niobium, another half-poisson, niobium, iron, antimony, and we dope with titanium. What we found is that if we increase the centering temperature for this material, we can have a significant performance gain by a factor of 2 because we have a higher conductivity. And then we want to see what can we do the similar realization, let's see, conductivity enhancement without the necessary to increase the grain size by increasing the centering temperature or whatever. We come up with the idea of indium antimony as a composite. And we can see for the same material, same processing, we can basically the grain size it's nearly the same before or adding indium antimony of the half-poisson phase. But other than that, we can see this indium antimony does not really dissolve into the lattice. And instead it forms this kind of particles and also aligns along these grain boundaries. And this of course, changes the microstructure. And it could also yield a significant reduction of the grain boundary of the resistance of the material in general. And also increases the power factor. Then we do characterization, and we can see the grain boundary mapping tells us that there is indeed an enrichment of indium and antimony, which corresponds to a depletion of niobium and iron. So basically, this is basically indium antimony there. And also following an atomic probe tomography, we also see that there is enrichment of indium and across the boundary. So that means we can effectively change the grain boundaries from a resistive one to a non-resistive grain boundaries to performance, increase the performance. Okay, so to make a conclusion, we can use this grain boundary. Let's see this. The model basically is called the scattering. To effectively reduce scatter the low energy charge carriers to promote the high energy charge carrier ones, and applies pretty well for high carrier concentration materials such as metallic, copper nickel, and degenerate semiconductor yttrium telluride. And we could also use coating these grain boundaries to boost the Seebeck coefficient. And we also found that grain boundary is not necessarily a resistive source, but also it can be much more conductive than the grain interior to promote the performance. And also, last but not least, grain boundary modification could enhance the material stability. So to make this technology more practical relevance. Okay, with that, I would like to thank my collaborators and also from Max Planck and also from Northwestern. And yeah, my team and also some funding sources. And I'm ready to answer your questions.
Thank you very much. Very interesting talk. With questions? Yes.
Maybe a question to the sizes. So you speak about grains, grain boundaries.
Yes.
What's the size of the grain? What's the size of the grain boundary? What is the mean-free path? Are we dealing with grain boundaries or are we dealing with the heterostructure?
Well, detailed microstructure I didn't shoot here. I think grain size is usually the level of, let's say, 1 micron. Grain boundary, the effective grain boundary depends on the doping level. I mean, higher doping, we have a effectively larger grain boundaries, but typically it's in the range of, I would say, tens of nanometers. So
Mean-free path of room temperature.
yeah, that's a this discussion we also involve a lot in the community because usually the charge carrier has much less effective mean-free path. And so the picture actually I think we have thinking is this mean-free path picture really valid for this material? I mean it's valid, but maybe it's the grain boundary itself that is very bad to make this scattering particularly stronger. And we of course, this is not something I can answer very well for now, but it's definitely a very interesting topic. Yeah.
But these are not metals. Yeah, it's like semiconductor. It's a semiconductor grains, right? Mean-free path is very small. It is less than grain boundary, I think, usually. And grain boundary.
The scattering length in any case smaller than everything, but introduce there. The whole notion of grain boundary. So in the grain boundary, you will have several scattering events. So therefore, it's not grain boundary. Grain has a lot of scattering there. That's my starting point. Simply have hetero material now.
Yeah, so maybe a comment on that is that the usual way to so the usual approach is that your mean-free path is smaller than anything else. But we see in many, and in some cases that holds, but in many others you are in between. You cannot talk of a heterostructure. This is you can define a potential for everything, but you cannot talk also of a mean-free path of all that. You are in between, and that's more better.
No, but it is the case that the conductivity of the grain boundary is better than of the grain.
This could be, we can do the modeling, and we can model this bit. I mean, maybe for example from here, this is some two-phase model, like is a series circuit, and we can extrapolate an effective grain boundary conductance and effective grain conductance. That's what we can do. Yeah. But from this result, we can get this result, but of course, it's real grain boundary conductivity. How do we measure that? This is very difficult.
And, could you just remind me, because I remember the figure of merit is very nice.
Yes,
it's
sir.
very important, but for people who are doing this stuff. But I never actually was interested in thermal properties.
Okay.
Therefore, figure of merit, it is the ratio of conductivity to
conductivity. Yeah. Seebeck coefficient square times the conductivity divided by thermal conductivity. And times the temperature.
Seebeck coefficient square. Yeah. Okay, but thermal conductivity remains the same almost.
Thermal conductivity varies because we are doping to the lattice. It also changes. But this case, we're more like saying in electrical. But thermal is not the most decisive contribution for this case.
I wanted also to ask about this formula about the Seebeck coefficient and about your. So this is the matter of the terminology, yeah. So, for example, we call Fermi level is zero. We put Fermi level to zero, but you in our language you're speaking about Fermi energy, right?
Yeah, yeah.
So, but in so many bands system, what is Fermi energy? You can show, for example, some electronic band structure. What is Fermi energy there?
I mean, maybe I can show directly to this one, right? Talking about.
Yeah.
This is of course calculation, and we don't have like dopants here. You change the dopants, of course, you change the Fermi level. But here is the top of the valence band.
But okay, this is I just do not understand much because I understand that there are many something which I don't know. But for example, if we consider it for metal. Yeah. And this formula means that if you have a symmetric band, like electron hole symmetry, you have zero as the coefficient.
It doesn't have zero because it's not really symmetric in real materials.
No,
if it's symmetric, then it should be zero.
Zero.
Yeah, it should be zero.
More questions?
That's maybe a very stupid question. When you try to dope this system that you put non-stoichiometric, say, to do them or so,
yeah.
Is it really a single phase, or do you have some unreacted yttrium that then?
At least from X-ray, what we can tell is same pattern. So yeah, there's not is changing, but the same looks like the same. So the symmetry is the same, so still keep the same symmetry. Well, until some degree, of course, we cannot go infinity. After certain levels, it's having purity peak lower.
Okay, maybe some more. So for me, so if we start from the metal, yeah, I understand that it is quite long mean free path, let's say, and the scattering, center of scattering would be different, but grain boundary is maybe the most important scattering. But if you start not from the metal, but from the semiconductor, why you are speaking in terms of scattering? I understand this because there's no free electrons for me. What is?
There is actually the doping level. We're still trying to
some doping level.
Yeah, we definitely have some doping to measure this conductivity. I mean, actually, is this stoichiometry, instrument 2 telemetry, we decrease the tellurium. We actually adding carriers into the system.
Mm-hmm. And these carriers and what in terms in terms of mean free path, how long is it?
That we have to calculate.
I mean, comparing to grain size. Grain size.
I think mean free path is still.
I do not have feeling about it because it is such a valued system. I could say about metals, but
in this particular, I don't know. I have not.
Yeah,
in the usual thermoelectrics, usually the Fermi levels of the last electron is already in the conduction band. So we assume that all electrons involved in the process are localized, so the mean free path is relatively long. Some calculations made for some typical thermoelectrics speak of in the order of 10 nanometer. In the order of 10 nanometer. But it's not like a typical semiconductor with the Fermi levels in the gap. So you really have the electrons pretty much localized to some place. Here we speak of quasi-metallic situation. So electrons have relatively long mean free paths and are essentially delocalized. So that's the usual hypothesis of working. In cases like that, where you have a lot of defects and stuff, I don't know. I don't know in that particular case, but the usual assumption is long mean free paths assume metallic properties. And definitely the Fermi level is in 90% of the cases way high above the conduction band and way higher, several 200 or 300 millimeters about.
But by saying sorry.
I think the cloud is bad metal. It's not really
Charge carriers are already in the level, I would say 10 to the 20 something like.
But what would be perfect material? The material is very conductive grain boundaries. And which parameters should
I think the really best for thermoelectric should have a low charge carrier, but with very small amount of defects.
Lower charge carrier.
Yeah, lower charge because we have higher CPEC, then you can preserve the feature of a high mobility.
Some materials like two-dimensional graphene, for example, it would be something.
We have a different.
This grains, it could be a very good material if you have graphene with conductive grain boundary.
Could be. I never deal with two-dimensional objects to work.
Okay.
Yeah, thank you.
Thank you very much. And finally, the last speaker is Nicolás Pérez. Yeah?
Sí, estaba en el otro lado.
So thank you very much, and thank you for having me here today. So since there was some interest in thermoelectric activities of thermoelectric materials from the side of our guests, so I will show some a summary. So it's kind of not a specific topic, but as more or less 1 or 2 slides per material, showing more or less the highlights of the research that has been done in my lab over the last years. No? So it's not a specific material, but a broad spectrum of different things, different techniques, and different motivations. So as already mentioned, it's not right. Okay. So unfortunately, as you see, this is the list of collaborators or people that have contributed some materials or some other things to this work. You see that most of them are facing to the west. So maybe from now on, I also partners facing to the east. But I cannot show the next one.
Just use the mouse. Maybe it's
yes. Yeah. So this picture has been shown already by Evgen. This is my group is called Transport in Thermoelectrics, and I'm the host group of the PPMs Lab facility, which consists of essentially 2 experimental halls with in total 7 PPM systems. So that's a lot of machines, and they give service to essentially the whole institute. So Institute of Metallic Materials, and we have also some significant collaborations with the Institute of Structural Physics, with which we share one instrument, which is that one is joint purchase. So in that sense, so my lab collaborates with a lot of people, mainly experiments from around here and other people that have been shown, or they all performed in this facility. And of course, upon agreement, we establish collaborations with people external to the IFW. A lot of people currently from TU Dresden, of course, other places around Germany and around the world, as you have seen in the previous introductory slide. Well, this is just some examples of things. Some of them will be shown later. So going to the examples, one. So here the motivation. So study glass rates. Glass rates are interesting materials for thermoelectricity. This is all somehow thermoelectric related applications or thermoelectric related materials. They are all bad metals, highly doped semiconductors of some sort, with a twist in any case. No, in every case has a different. In this case, it's a glass rate, essentially a gallium germanium structure, like a structure. Glass rates are usually good thermoelectrics because they have this what we call glass property of thermal conductivity. They have extremely low thermal conductivity and metallic behavior for the electrons. The game here was to introduce a magnetic component, and the question proposed by the collaborator in Florida was to study if there was, due to magnetic ordering, which happens in this material, if there would be some change in thermoelectric properties. We were expecting to see some change in the Seebeck coefficient. We didn't find much of it, but what we saw was a strong reduction in the thermal conductivity when the material became ferromagnetic. So the glass rate, if you know, is a cage structure, so with gray voids where nothing is, and inside these voids you may place some things. In this case, it's europium, which is magnetic, gets ordered, and we assume that the magnetic ordering is not only just between the europium atoms by themselves, but there's some degree of mechanical or mass coupling to the lattice or to this volumetric case structure, leading them to a strong reduction in the thermal conductivity, which then is interesting by itself. Collaterally, or in the course of these investigations, we did the full program fit. We measured resistivity, we measured cell coefficient and capacity. And on the way there, we found out that the magnetic ordering was going through some glassy structures, a spin glass kind of transition or situation before getting them fully long range ferromagnetic. So, example number 1. Example number 2. This is another interesting or potential good thermoelectric. This is a simple phase, in this case, calcium antimony, and here the motivation is to study chemical properties, or how chemical bonds affects the thermoelectric properties. This material is composed essentially of these chains that grow in the crystallographic Z direction, and this is covalently bonded in structures. They bundle up in the plane that you see in the top, but this bundling up is ionic. So you have two different type of chemical bonds in different crystallographic directions, and supposedly this should lead to changes, to different changes or different values of the relevant properties in these two directions. And here the example goes about the technical issues that we found here. Is these crystals can be grown as needles, but they are in this case they are undoped. This pretty interesting material, so they get very resistant. So the strategy to get the measurements done was to reduce the size of the material and fabricate lamellas with the focused ion beam, and then fabricate longer structures on top of them, and then perform the measurements. We were partially successful. We didn't do all what we wanted to do, but at least the conductivity and the Hall effect could be measured in two crystallographic directions, showing essentially an tremendous difference in resistivities or the superconductivity. And that was the story that time. So in this case, the question was probing anisotropic properties to chemical characteristics, and the strategy to get in the measurement was to fabricate flip caps out of single crystals. Next example, here we have a very good thermoelectric, the material that is currently used in all Peltier coolers and things like that, so bismuth telluride. In this case, the question was to study not only not the material, but how the nanostructure that was created by the colleagues, how that affects the transport, or how electrons move along this particular structure in an otherwise very well-known material. Yeah? And here the structure is an array of nanowires that go vertically, like in the vertical of the image of them, but with the characteristic that they have nodules that connect the wires horizontally. Yeah? So in that case, you can measure that array as a whole, as it would be as in film. Yeah? What we saw, we did several things, and so to make the story short, the resistance follows the Anderson localization model in the transverse direction, and so which is partially or mainly due to confinement effects in these constrictions. And another thing that we saw a little more interesting is weak anti-localization feature in that nanostructure has a weird shape to it. You know? So usually weak anti-localization, you have maybe polar shields, same parabolic, whatnot, and at some point you enter into the localization regime and you have one dip. In this case, there's two dips. You know? One, and then a second very pronounced. Question. So what we did is then, and this is the example here, is how to go into that. So we perform angle-dependent measurements of that object, shown on the picture. And then we studied the evolution of this magnetoresistance signal of these two dips with the angle to the magnetic field, right? So, and in one case, we saw that the lower dip or the internal dip scales with the cosine, also the vertical projection of the magnetic field, and the other scales or collapses with the sine of the angle. So that gave us the idea that these two dips or these weak anti-localization features are related with two geometrical directions in the perpendicular directions in the structure, which according to what it looks like, it would be vertical along the wires themselves, and the other one transversal from wire to wire in what more or less looks like a cheese or Swiss cheese kind of structure. So again, so the details we can discuss later in the discussions afterwards. So here a little bit of research of us. So this is more in the line of work that Ran showed before, studying scattering mechanisms, mean free paths and all that stuff, how that affects the performance of thermoelectric materials. Of course, my colleague Ran works more into more applied materials, so he just tries things on materials that are already very complex. I'm more a nerdy physicist, like that, so I want to make it more simple. So for this particular study, we started with, and this is very topic. We started with something which is pretty simple in comparison to things, which is this one. So it's pretty well known, and for what it is, it's electronically simple. It has a relatively wide bandgap, and all the properties come from only one band, although it has many bonds. So not too difficult. So we made a composite out of it. In that case, changing the structure of the polycrystal fabric. In one case, we arrange things so that we get a polycrystal, but with a highly textured microstructure, following the z-axis. You see these lines, or these slabs are perpendicular, are AB planes. So the material consists of polycrystal grains stacked up in the z direction. We change things, and then we start adding some other crystal orientations, and then we end up with something which is pretty random. All directions crystal orientations are present in the carbon path. So that has as a consequence that the resistance changed significantly. Not so much the carrier density, there's minimal changes into the factor 3 or something like that, but the conductivity changes. Of course, we studied what would be the relevant parameters of that, scattering factors, temperature exponents at high temperatures. So for the layer structure, the main scattering factor is electron-phonon interaction, pretty normal. For the others, you have more. You have more intense scattering, so a more intense power factor than not as would be only for electron-phonon scattering. So you have additional impedance due to the orientation of the grains. Yeah? So to link that to thermoelectricity, of course, and this is there are other reports on bismuth telluride and other materials that share this tetraimide structure. So for tetraimide materials, it's pretty common, or has been after that pretty well established, that you need to have, in order to have high conductivity, high electrical conductivity, and then to have better performance, you need to have a certain degree of ordering in the composite or the polycrystal that you fabricate. This was important in its moment some years ago, because the trend back then, the community, was to nanograin everything. Nanograin everything because you reduce strongly the thermal conductivity, and that should be better. No, sir, it's not, because you have collateral effects, and in particular in the most efficient thermoelectrics, this type of materials, that's what you don't want. You want to have a compromise between the reduction in thermal conductivity and the possible reduction in electricity. So we did that. Following this idea of scattering centers, and that because we knew bismuth selenide so well, we added the next complexity level, is at a secondary phase, more or less in the same direction that Ran was doing, but now with kind of adding complexity incrementally, not just all at once. And in that case, we worked with a secondary phase to create scattering. But in this case, it was an insulating material. We tried several ones. I showed the ones that we understood, which is the iron oxide. So why we use the insulators is because to avoid the question, if we have a metal or something conducting in between, what happens? So we put something on purpose which is not conducting, although there is a slight conductivity for this iron oxide. But anyway, in there, and see what happens. So we proceed with the usual program, and then we found something particularly interesting, which was not what we expected. In this particular case, this image here shows a compositional map of what would be the transition from iron oxide to bismuth selenide in this case. And what is shown here, this is the two lines. One is from the iron and oxygen, very sharp transition before we have the oxygen and water. And the purple line, I think you see it as purple, is the bismuth. Surprisingly, for this type of composite, what occurred in doing the composite is that we have a gradient of composition in bismuth. Probably due to an electrochemical effect related to probably the oxygen or the iron and the oxygen that draws bismuth from the inside of the grains to the part closest to its attractor, more like that. And that changes a lot of things. That changed a lot of things. Because we knew the starting bismuth selenide, how it was, what was the chemical composition and structure and defect structure, we could pinpoint this or follow the lead of the bismuth gradient composition and translate that into defect structure composition. So usually in these materials, there is a balance between antisides and vacancies, anion vacancies and antiside defects, which is more or less balanced. Because we have compositional gradients, this balance is unnaturally biased, creating two things, which we then could rationalize with calculations, or with the help of calculation factors, which was that defect structure, this balance between antisides and vacancies gets disrupted, creating, in all cases, an increase in free charge. They are all donor type. The imbalance results in donor type defects, in donor type situation, creating an excess of carriers. So we ended up doping our materials without doping it. It's just a modulation, a compositional modulation in length scales of 50 nanometers, something like that. In that situation, we had a tremendously increased electrical conductivity. You see it in the red dots, up to a certain amount of the secondary phase of the iron oxide. Because after that, when you have too much insulating phase, then things start to go bad again. But up to some point, we profit from this chemical effect and increase the conductivity largely. Because of, and that's why however, the CEVEC doesn't follow the trend as one band semiconductor if you change the number of carriers. It doesn't. It's better than the tradition. Probably because it is not a homogeneous long-range topic, it's a homogeneous. I would say there is not a periodic potential for all the material, but only partitioned in regions of about 15 nanometers. So creating them a less than expected reduction in the CEVEC coefficient. All things put together means that this bismuth selenide, which is essentially the same as the one we had before, but with this added component, performs better for thermoelectric reasons, especially for the heavily increased thermal conductivity, electrical conductivity, and the not so deteriorated CEVEC coefficient. So you see a number of examples from a number of materials with different approaches. Lithography, focus ion beam, just bulk measurements, all at low temperatures, with magnetic field, without magnetic, whatever, for different motivations. So I thank you for listening me out these the minutes, and I hope that we can discuss further later on.
Thank you very much. Questions, please? From my side, the first question, so this is compounds bismuth to selenium-3 into 3 systems. These are systems which are studied as topological insulators, right?
Yes.
What is the difference? Why they grow in nanorods and not in lakes?
That wasn't done on purpose. That was because they were grown inside a template.
Inside of
a template. And so a template was created on aluminum oxide, which contains the holes where this grows then filling this hole.
And here axis is along.
Yes.
And then the more natural question for me would be then if you're speaking again with grains and grain boundary, what about topological surface states?
Yes, complicated. Yeah, this is not included in here. In this summary, there is some effect.
It should be topologically protected.
Yeah, well, so these materials are extremely disordered. So we did not measure, so flakes of these things, nano layers have been measured a million times. No? But nonetheless, it's not presented here, it's measured, I can show you later if in the discussion. There is, we can see localization effects in these composites.
Localization?
Yeah, with localization effects.
With the surface on the boundary?
In the whole thing. In the whole thing. So we measure the whole thing. We don't need to reduce the dimensionality.
So it is strongly disordered.
Yes, exactly. So so phenomenology. So from the appearance of it, from the appearance of it, we see the same localization effects as you would see in a nanostructure like that. Well, not that particular, but that same. No? And the key is to create that type of structure. If we have this type of structure, our working hypothesis at the moment is that we have two things happening at the same time. We have, of course, bulk carriers, so band conduction, normal band conduction, that dominates. In that situation, because we have a strong impediment to bulk conduction, another part that is also existing in this particular material, which would be surface states, which have plenty of surfaces, somehow they start to show. Surprising for us is to evidence that it is not a surface to the vacuum, as is normally predicted, but it's surface to itself. So we think, and it shows, we can show it later, we think that the touching points in this type of materials are kind of vacuum enough to start showing. In the case of the guys with the iron oxide, there is more to it, because the localization phenomenon changes with the amount of iron oxide that we put in there. And the thing is, the more iron oxide we put into it, the localization changes from weakened anti to weak localization. Well, the shape of it. What they would say is that the spin orbit constant changes from positive to negative. So that's so. And because and that points out to a certain interaction from a magnetic component to something close to the surface, close to that area.
But properties of the bulk of the material. These grains are large enough to consider that they have electronic structure, right? And there's actually Dirac forms, and that they are actually very sensitive to the doping levels.
Yeah.
It could be.
That's a good question. Yes, I would like to work on that since it's time. Yeah, but this is the key problem. So wrapping up is, we see that there is, when our material, the thing that we do contains more surface.
Yeah, I understand the surface.
The phenomena associated with usually surface states, like localization, show up more intensely. The moment that you add a second component, in this case, we play also with silicon oxide and so on, then you change the appearance of that things. So there is something going on the surface that might be probably related to some inherent properties of the resource.
Yeah, but clearly the surface dopes also the volume and the changes. Actually, that for previous talk I said about graphene, but first wanted to suggest the topological insulators so that they have conducting grain boundaries. But it could be so you can tune them very much if you can. More questions, please. It's yeah. Actually, I also wanted to ask about this interest on the first slide. I think it is interesting for me because we got from IFW the magnet, and we have now the possibility to measure until 16 Tesla, and therefore the actual effects interested. So what is I saw just like that. Okay, I saw somewhere very strong dependence on the magnetic field, and this is, say, probably about the thermoconductivity. Yeah? Thermoconductivity and as function of magnetic field, but doesn't matter. Actually, what is the mechanism for strong reduction with applied magnetic field?
And we don't know exactly, because we wanted to do some synchrotron measurements with temperature, in cooling down 10 Kelvin or something like that. And we did not do that, but so according to the capacity data, so we see here, so from here to here, there is a scale. Not here. Here is thermodynamics. This is not. So, in the capacity, we see that there is two positions where things happen. The ferromagnetic transition is essentially here. It's long range ferromagnetic order. We think that this is short range ferromagnetic order. That is the AC susceptibility kind of shows this spin glass type of thing. That's it. So the reduction of thermal conductivity starts already here. So the material doesn't need to be long range ferromagnet. So short range ferromagnet already works. So what is the coupling between this shouldn't be an electronic thing, so it's not a reduction of thermal conductivity due to conduction of electrons, which they exist in this material, because the trend goes in the other way. So the material becomes more conducting. So the thermal conductivity should go up by that reason. It does. So it needs to be a structural lattice or phonon-related issue. How can we create stiffening or the coupling of the phonons? There are different hypotheses at the moment. One would be kind of the europium gets closer to one side of the wall of the cage. So you assume the cage is kind of an octahedron, if I'm not wrong. And usually you assume that the europium is sitting in the middle. If it goes to one side, because it starts to see another europium somewhere, and they come closer to each other, Europeans come closer to each other, and European comes closer to the cage, maybe disrupting the natural frequency of the cage. So that's one hypothesis. But we want to do the synchrotron. We didn't do it.
It's complicated.
It's complicated
because I thought that if you have some ordering, then you have, in addition, let's say, magnets.
That's the next thing, exactly.
Increase.
That's the thing. So we could not, from our data, we could not fit 20 Magnum models to data, and difficulty spreads a lot. So it's difficult to do that. We try, but it doesn't work. But it could be also a thing that you have a Magnum. The thing is, if it's Magnum, why does it start when the material is short range for a Magnum? It tends to be a very strong localized Magnum or very strong. It's very stiff.
Thank you. Maybe more questions, yes. Then let's send speaker again. I think I'll probably say a couple of words about what's happened. Actually, I see no questions also from online, which is a pity. Actually, it is another question that we should organize this seminar somehow, that should be coordinator in both on both sides, and to keep it because somehow I see that this communication usually does not work as I would prefer, because usually. Okay, so but I'm sure that people there have a number of questions, but should be someone who coordinated. It is my fault. Okay, so I wanted to say to thank all of you for this nice, as for me, workshop, because we had several ideas, or at least directions, which we wanted to cover. First, about sample growing. Sample growing, it is we are grateful. It is nice. I learned actually a lot with communicate and with the talks, and with communicating with people, and with Andrei Maluk also, because and I think actually the main conclusion that we should start to try to grow BISCO with optical furnace, and it is promising. And actually other materials, of course, we should discuss, and I understand some problems and how it is. Then let's say theoretical part, it is which is a core of our project, is theory-assisted search for new materials. And of course here is we remind us about possible, let's say, which they almost close, but maybe still interesting firms, FST or FTC, firm selenium tellurium could be an interesting example. And actually, this is search for topological superconductivity, right? Except platinum bismuth, it could be some interesting examples still. Okay, and it's interesting really for us, this combination to go to machine learning stuff and to combine what was presented by Isaev and Feya and Alexeya. This is try to include this machine learning algorithm to this band structure calculations. And actually, we have now very nice example recently. One of our new students, he did it as bachelor project, but it appeared quite simple for him to just to predict superconductivity on the material research database. Yeah, how it's called. And he is not very like his result because it's only, let's say, 78%, but I think it is quite promising that combining with the knowledge of what we think is important in electronic structure and how we know the difference between calculations and experiment could be promising direction. I thought it was much more complicated than he demonstrated it works. Here we covered it. We do not cover it, but machine learning mentioned only shortly. But also I think interesting materials are really it is flat band materials, and Igor tried to make some summary about it. It is but only for one direction, but we know many compounds with, let's say, weak superconductivity, but weak anomalous superconductivity. This is twisted graphene, very known example where due to flat bands, we have superconductivity. And it is, even if you remember doped fullerenes, it is also the system where superconductivity appeared on quite large unit cells, and I think these materials like this is LK99, yeah, which is not promising maybe for superconductivity this exactly compound, but the whole systems could be interesting, and there are many systems which with many flat compounds. I think this direction we could pay attention for it. Okay, so and finally about this last session, I think we will try to develop. I'm looking for this laptop. It would be interesting because we also have equipment about this and maybe some interesting stuff. But also I wanted just maybe to discuss, or maybe later, but I want to mention this idea which Evgen Len presented, not idea, but about just reduction of the work function. Reduction of the work function, I think we could discuss with York. Maybe he could give experimental points from experimental point of view, some ideas. Because, for example, in Fusuma spectrometer, for example, we have laser, we would like to decrease the work function of the spectrometer. I learned from the beginning that you measure the Fermi function of spectrometer, of the work function of the spectrometer, not the work function of the material. But it's not very correct also. And the question what we should do maybe with spectrometer to lower the work function. And the question was if we for example make evaporation of cesium of the whole chamber, this probably lowers the work function of the whole spectrometer as well as. But okay, this is different stuff. But I mean that even this stuff is interesting for us. Okay, so I thank you again, I thank Sylvia very much for this organization of this workshop. It was very short notice, and we decided to do it in a week or two. And I thank you for participation. Thank you.